Thank you. So I'll be talking about subseasonal forecasts of opportunity identified by an explainable neural network. So first, I'll briefly talk about subseasonal timescales. So here I have a schematic of prediction scale versus prediction lead time, where prediction scale is on the y-axis and prediction lead time on the x. On these weather timescales, or hours to about a week, we have relatively high prediction scale, but this rapidly decreases towards these subseasonal timescales, which are these 2 weeks to 2 month timescales. And then again, we have some prediction scale that pops up on these seasonal outlooks due to phenomenon like ENSO or ocean circulation. But our lack of prediction scale on these subseasonal timescales is really due to minor errors in initial conditions that can lead to chaotic growth over time. And you can think of this like the butterfly effect. So to help improve subseasonal timescales prediction, we can look towards forecasts of opportunity. So forecast of opportunity is this idea that certain conditions can lead to more predictable behavior than others. So beyond these weather timescales where we have relatively high prediction scale, we must look for specific states of the Earth system, or these opportunities, that lead to enhanced predictable behavior. This is nicely explained in Mariotti et al. 2020, and Albers and Newman use a linear inverse model to identify forecasts of opportunities. So one of these opportunities is known as the Madden-Julian oscillation, or the MJO. The MJO is a convective dipole that propagates from the Indian Ocean into the Central Pacific Ocean over about 20 to 60 days. This dipole is of convection, where we have these clear sky regions in brown, and then this enhanced convection in a teal bluish color. And using, when the MJO is active, we can use information about the state, or the amplitude and location of the MJO, which is denoted by its phase, to predict what will happen in the US or the North Atlantic or Europe in the coming weeks. So for example, the MJO has been shown to change the storm track, which has led to decreased AR activity or increased AR activity, depending on where you're looking, over the United States. However, what makes the Madden-Julian oscillation, or the MJO, an opportunity is that it's not always active. And so when it is active, we can harness our knowledge of its state and location to improve our prediction skill of certain variables. So where do neural networks for subseasonal prediction come in? So how can we utilize neural networks to identify forecasts of opportunity for subseasonal prediction? So I'm going to briefly talk about what neural networks are, or specifically artificial neural networks, just in case some people aren't familiar. Normally in our field of atmospheric science, we think of neural networks as this black box where we put some data in, something happens, and we get a prediction out. So what's actually happening with an ANN, or an artificial neural network, is we're inputting some inputs, x1 and x2. These are multiplied by some weights and summed together in what we refer to as a node. And you might recognize this so far as just straight linear regression. What makes an artificial neural network nonlinear, or a neural network, is this activation function. This activation function acts as a nonlinear mapping of our linear regression, so that we can account for nonlinearities within our system. So training a neural network is merely trying to identify these weights and biases that optimize our network. So as you can imagine, we can have many, many inputs. We can have many nodes, which are these gray things, or gray circles. And we can also have hidden layers, which each layer consists of many nodes, and there can be multiple layers. And then we have these outputs, which are referred to as our predictions. So as I've said, we have this data. This can be put through a very complex network, and this outputs a prediction where we've learned these weights and biases that lead to accurate predictions. So the complexity and nonlinearities of our ANN allow us to learn many different pathways of predictable behavior. And once this model is trained, we have an array of weights and biases that we can be used to apply to predictions of new data that the network has never seen before. So the question that I'm trying to answer today is, can neural networks identify forecasts of opportunity for subseasonal prediction? So I see this as a two-part question. The first question is, when. Can neural networks identify when we see periods of enhanced predictability? And then the second question is more of a science question, which is why? Why is there predictability in the first place? And how can we apply this in the future? So for our problem, we use outgoing long-wave radiation in the tropics as our input, where you can see here's the outgoing long-wave radiation and our input layer. This is passed through 2 hidden layers. And we are trying to predict the sign of the circulation 3 weeks later over the North Atlantic, this red dot here. And this is a binary classification where we're trying to predict the sign. So either the sign of the circulation is positive or it's anomalously negative. So how do we determine when? When do we see periods of enhanced predictability using a neural network? So to do so, I use something called a softmax activation function. A softmax activation function is applied to the last layer or the output layer of the network. So let's say we have an output of 3 and 1, where the network is predicting a positive sign prediction of the circulation over the North Atlantic. What we can do is we can put these variables into the softmax activation function, and it outputs this thing we refer to probability or confidence. We refer to it as a probability because these numbers sum to 1, but I will refer to it as a confidence for the rest of the talk. So I refer to this to a confidence because we can interpret this as the network is 88% confident in its prediction that this will be a positive sign anomaly. Now you may see where this is going is that high confidence predictions, when the network is really confident in its prediction, this may indicate that we have a forecast of opportunity that the network's identified. So to see if this is actually the case, I've taken a trained model and I've plotted the neural network confidence threshold on the x-axis and accuracy on the y-axis. So when the confidence threshold is relatively low, you can see that our accuracy hovers around this 55 to 60%. But as we keep increasing this confidence threshold, we can see that our accuracy starts increasing drastically. And we would expect this. As I said, we have phenomena like the MJO in the tropics, the specific region that we're looking at. And so as confidence thresholds increase, our accuracy is also increasing, which suggests that our model is finding these forecasts of opportunities. But again, this is an opportunity because as we increase our network confidence threshold, we're also losing samples that we can use. So when do we see periods of enhanced predictability? We can use model confidence to identify this, or the softmax activation function. But why? Why is there predictability in the first place? And I think this is where the really interesting questions come in. So to do this, we use Layerwise Relevance Propagation, or LRP, which basically asks the question, what did the model learn? So in our case, we're asking, what are the relevant physical structures of OLR, our input, in the tropics for prediction of the sign of the circulation over the North Atlantic 3 weeks later? So Layerwise Relevance Propagation uses a trained neural network. It takes an input, let's say, of a cat, and outputs a prediction. Let's say that the network correctly predicted that this was a cat. And we wanted to see why the neural network thought it was a cat in the first place. So what we can do is we can take our prediction, our correct prediction of a cat, we can back propagate this through the trained neural network, and we create this heat map of relevance, or where the network looked to make its accurate prediction. So you can see in this case, we have the head of the cat outlined, specifically the ears, some whiskers, the nose, and this is where the network looked to determine that this was a cat. So in our case, we take outgoing long-wave radiation, we pass it through some hidden layers, and we get the sign of the circulation 3 weeks later. So let's say, again, that we're going with the network predict a positive sign circulation. If we apply LRP to this question, we're asking, given that there's a correct prediction of a positive sign circulation, what did the outgoing long-wave radiation look like 3 weeks earlier, and what were the relevant regions in this region that were important for this correct prediction? So what are these relevant physical structures of OLR in the tropics for prediction over the North Atlantic? So what we've done is we've taken composites of the correct positive sign predictions over the North Atlantic, this spot here, and we've plotted the relevance and shading, or the important regions for this prediction, and then in contours, we've plotted the anomalous OLR. So you can see in the The dashed lines is where we have enhanced convection, and the solid lines is where we have suppressed convection. And this looks a lot like MJO phases 3 and 4, where the relevance is highlighting this enhanced convection over the maritime continent and the Indian Ocean, and then some suppressed convection over the Western Pacific. We can do this again for a negative sign prediction, and you can see that the network is identifying the enhanced convection, or the suppressed convection over the maritime continent, and the enhanced convection over the Western Pacific. Now you also see this hotspot that's just located west of Hawaii, and we wanted to examine this a little bit more and why this region was coming out of our analysis. So what's really cool about layer-wise relevance propagation is that for each individual input that we put into our network, we get a unique relevance map for it. So each prediction has its own relevance map. So what we can do is apply clustering to these LRP maps to understand if there are many types of relevant structures that lead to our enhanced prediction skill. So for example, if we look at these negative sign predictions where we had this hotspot over Hawaii, we can see, or west of Hawaii, we can see that the first cluster of our negative sign predictions has this MJO phase 7 and 8 structure, where we have this suppressed convection over the maritime continent and enhanced convection over the Western Pacific. But what's interesting is that cluster 2 is specifically looking at this hotspot just west of Hawaii, which could be possibly a new forecast of opportunity for this region over the North Atlantic. We can also apply this to positive sign predictions. So for cluster 1, we see that this looks a lot like MJO phases 3 and 4, where we have the enhanced convective region highlighted and the suppressed convection region highlighted. And then we can see in cluster 2, the network is specifically highlighting this one region of enhanced convection over the maritime continent, where this convective dipole looks a little bit more like phase 4 instead of phases 3 and 4. So you may have noticed that there's also this hotspot region that's in the corner of this map. So we're thinking that this may be associated with the connection between the MJO and NAO, the North Atlantic Oscillation, and then the North Atlantic Oscillation's role in possibly initiating MJO events. And this could be the signal occurring within our model. So clustering can be a useful tool for identifying one or more of these forecasts of opportunity. So why is there predictability in the first place? Where is it coming from? We can use layer-wise relevance propagation to address this, and we find that this predictability is coming from the Madden-Julian oscillation, and then also we find this new forecast of opportunity located just west of Hawaii, which may also be used to increase prediction skill over the North Atlantic on 3-week timescales. So in conclusion, we can use neural networks to further understand subseasonal prediction, but this is not just limited to these subseasonal timescales. This could also be applied to other timescales on shorter timescales or even longer. We can use model confidence or this Softmax activation function to identify opportunities for increased accuracy or enhanced prediction skill. And then we can use layer-wise relevance propagation to really ask those science questions about why the network had an accurate prediction. So it really opens up this black box that we've always considered a neural network to be. With that, you can find, this is currently on arXiv, and you can find it here. We also have other papers from our group that have been published that you can look at here. Otherwise, if you have any questions that I can't address today, you can email me or find me on Twitter. And then I can take any questions.